image. That is changing the lighting, changing the white balance, and modifying values of each color channel. Some newer methods to do data augmentation for computer vision are so-called cutout. It's an occlusion method. So basically the augmented image will be the original image with a patch of it removed. And also more recently there are ways to discover optimal data augmentation strategies for a given problem that is not doing it manually, and they prove quite useful. Yeah, you should take into account the fact that some augmentation, some altering of the image or of video maybe could be invalid for your problem, depending on the problem at hand. For example, it's not really optimal to, for example, change the color space of a cell in case that you're doing medical image analysis, or alter too much the color space of the frame that you take from the camera on board of a car, maybe creating a data set for self-driving cars. So consult with subject matter experts before doing some significant data augmentation. Yeah, it can be really thin here because of the light, but here is a sample of different kinds of augmentation of a single image. It's a hedgehog, I guess. Okay, moving on next. So, like last 4 years, maybe, a technique called transfer learning emerged. And basically it means that you take a pre-trained model and you just fine-tune it on your data set of interest. Depending on the data set of interest, like how close it is, like its data distribution to the data set the original model was pre-trained on, you should either fine-tune like last layer more aggressively in case that the distributions are similar, or you'd have to fine-tune more layers out of it and then possibly fine-tune the whole network. So as a rule of thumb, if the target data set is close to the original data set, you can fine-tune just the last layer and you need less data. But if there are more discrepancies between these two data distributions, you need to provide a couple of heuristics. Heuristics are like some rule of thumbs or some functions that approximate how they would actually label the data. And then the snorkel system tries to use these functions to label the unlabeled data set, and then like somehow communicate to the model that is being trained that okay, this data is not well labeled, so beware. Yeah, so as I said, weak supervised learning or weak supervision is quite an umbrella term, and because of that in different literature you might find that transfer learning, semi-supervised learning or self-supervised learning are under this term, but it depends. Now that I touched semi-supervised learning, I should give you the core understanding of what it is. So semi-supervised learning means that you try also to use the unlabeled data set that you have, but you use it as some sort of structural prior for your problem. That is, the learning algorithms try to use the unlabeled data to understand better the underlying distribution of classes in your data set. That if data points are close to each other, that means that they might be related. Another assumption would be cluster assumption. That is, data points in a classification problem usually try to clump together. And the third one is the so-called manifold assumption. That is, derived from the first two. Manifold assumption means that it is possible to find a manifold in the data set, usually a high-dimensional data set, that is of much lower dimensionality. For example, in case that we are doing a problem of face recognition, the number of pixels and the search space for them is really huge. But mainly we are interested in a few features. So manifold in this case would be the underlying space or surface, actually it's more like a surface, on which the data points of interest are lying. And if we can find this manifold, then we could efficiently solve the problem. Well, to some point, because there is still noise in our data, anyway. Okay, so a number of semi-supervised techniques that emerged recently are mix-match and unsupervised data augmentations. They are both from Google Brain, and they are using in quite interesting manner data augmentation, unlabeled data set, and a combination of loss functions for labeled and unlabeled data. In case of unsupervised data augmentation, the idea is that we have the same model trained with supervised, with labeled data, and we use cross-entropy in our case. But we also use this model to assess how the predictions on unlabeled data change as we use data augmentation. And basically the loss term for unlabeled data would be how consistent are the labels in case that we try to augment the data set. And then we combine these two loss functions and we can more robustly train our machine learning model. Yeah, and this kind of training is actually quite generic. As you can see, this image is taken from their original paper, and in their experiments they are trying it with both text and visual data, and in case of text they do translation and sentiment analysis, if I'm not wrong, on IMDb dataset. So the other one that I mentioned, mix-match, it's a bit harder. The idea is you get a batch of labeled and a batch of unlabeled data. And then you augment your labeled data because you want to provide this regularization by augmenting your images. In case of unlabeled data, you do a number of augmentations. That is, like, for a single unlabeled image you get, let's say, 10 unlabeled but augmented images. And then you use your existing machine learning model that you are trying also to train in order to predict the classes for each unlabeled augmented image. Then you average the prediction, and it's also used some sort of sharpening, so that you don't get a smooth, let's say, probability for each class, but a more sharp one, so that you can pin a single label on your unlabeled image. So this way the model tries to guess the actual label of the unlabeled image and subsequently use it for training. And after that, a technique called mix-up is used. The idea of mix-up is that you linearly combine two data points, and the assumption is if they are combined linearly, their label should be also a linear combination. So they are also using this mix-up in order to provide a more robust training. Okay, self-supervised learning. This one is quite interesting. So a couple of years ago, Joshua Benja said something that, like, intelligence is a cake, And unsupervised learning is the cake itself, and then supervised learning is the icing on the cake, and reinforcement learning is the cherry on top. But because the unsupervised learning is quite an obscure and it's also an umbrella term, recently he switched to so-called self-supervised learning. So self-supervised learning means that you are trying to get a supervision signal from the data itself, thus making the model to learn from its own data. And in this way, it seems like an unsupervised learning because you don't have an explicit label, but you still have a supervision signal, that's why it's supervised. So as a middle ground, it's called self-supervised learning. For image data, it's quite developed, and the techniques usually involve having an additional task or doing pre-training, where the task is, for example, trying to color the image. So you pass an original unlabeled image, and then you make it black and white, and then in the end you ask the model to color it back and assess how it colored it using the original image that was initially colored. Or another way would be, for example, to split the image in 9 and ask the model to order this batch of 9 crops of the image. Thus, it's trying to solve a sort of jigsaw puzzle. And so on. So it's really up to you how you model this learning problem. In the case of video signal, you can also try ordering frames. Or, for example, asking the model, is this sequence of frames valid or not? So for more information, there is a reference, it's from Andrew Zisserman and his slides from EML summer school in Bucharest that was last summer. Yeah, a note on all this something supervised learning techniques. A good idea is to try to use them in combination with actual supervised learning technique, like generic, where you have labeled data and you try to train the model. This is sometimes called multitask learning because you have multiple tasks. For example, in case of self-supervised learning, you can provide an additional loss function for the model to try, for example, to fill in cropped images or to do coloring. Plus the original cross entropy for predicting the label of the labeled image. So thus you can have a more strong supervision signal, and you can also learn, let's say, important and transferable features for your data points. Yeah, now the topics that are not so much discussed in the paper but are mentioned because they are really important. One way to do machine learning with little to no data available is to use the so-called active learning. So the idea of active learning is that you get the probabilities or the confidence of a model for each label. So a data point is passed through the machine learning model or deep learning model, and you get that, okay, for example, a specific image is a certain class with some probability. If these probabilities are low, that is, the model is not very confident in its own predictions, then a human labels these data points. And then they are passed back to the model now as training data. The assumption in this case is that the most important things for machine learning to learn are the points that are hard for it to understand. That's why usually active learning makes it possible to learn with significantly smaller data. Because the paper doesn't really cover this domain, because it's quite huge, I included in the slides this link. It's from Fast Forward Labs. It's a Cloudera laboratory for machine learning and data science. And recently they did an overview of active learning techniques, and they also have a demo where you can play around and see how different kinds of active learning lets you learn from up to 8 times smaller data sets. Yeah, and finally the so-called few-shot learning. So few-shot because there is few-shot, there is one-shot learning, and there is zero-shot learning, which is actually an entirely different thing. The premise of few-shot learning is that you want to learn a robust model from few samples, where few is less than 10. In case of one-shot learning, you want to learn from a single image. And in case of zero-shot learning, you want your model to be transferable to a new unseen class. So few-shot learning is more an initialization problem, and it is usually solved through meta-learning techniques, where you have a model, you train it on a lot of different small problems, and then you test it on another set of problems. So you're learning a good initialization for your machine learning model. The problem with this approach is it's not yet used in practice, because it's still a very nascent, it's still a thing of research, and there are no practical applications for now. It's not stable enough. The other techniques are used in practice. And yeah, some closing thoughts. Usually a combination of these techniques works best. For example, you can combine the knowledge distillation with data augmentation, or as you've seen in case of mix, match and unsupervised data augmentation, they actually do use a combination of them. Also multitask learning that was mentioned in the slides is also a very handy technique. And Snorkel also has in its recent update the capability to do this sort of multitask semi-supervised learning. So you should actually try that. And you should also remember that these are not all problems. You can still solve a problem with not having enough labeled data but still learning a useful representation. But then you have to take into account minority classes for which it's hard to get data. And it's quite a serious problem. I mean, you don't want to be in the situation of social sciences, where there is a joke that social sciences is more about the behavior of mainly white, upper middle class students of psychology and social science in Western countries. Yeah, and all the techniques outlined above, they cannot be used for really small data sets, where you have, say, 5 or 10 images per class. You need at least 50, but that's roughly. Usually 100 will do good. For less than that, you should focus on few-shot learning and maybe try to make it more robust. That's it. Any questions?
Thank you for the presentation.
Can you share your presentation?
Yeah, sure, I will. How do I do that actually? On the site or maybe on the Facebook page? You can put it. Yeah, sure, of course.
One more
Yeah.
question. You presented all these methods for image recognitions.
Yeah, I try to focus just on image recognition, but let's say most of them, actually all of them, can be used for text or tabular data or videos or whatever.
I'm actually interested in text.
Okay.
Can you say what methods?
Okay, if you want I can go through all of the techniques and explain how they work for text. Because currently I'm actually working with text, I use a couple of them. So let's start with active learning. You can use, as I said, a model, get predictions from it. The predictions that are having small confidence, for example, for, I don't know, sentiment analysis, where the model is not sure it's good or bad, then you as a human in the loop of this system, you get this data point and you label it, and then you add it to the training set. In case of multitask learning, recent advances in natural language understanding and language modeling mainly from OpenAI it's GPT, and from Google it's BERT. So these are very big neural networks that try to do a lot of things, and they are quite transferable. That means you can do transfer learning with them, the one outlined above. They are actually trained using multitask learning. So in case of BERT, for example, the model tries to fill in missing words. So it gets a big corpora of text that is unlabeled. I think they use some text from the web and Wikipedia. So they randomly remove words from a sentence or from a chunk of text, and then they ask the model to put it back, to fill it. Other than that, like this is one kind of self-supervised learning because the text itself provides the supervision. They also use next sentence prediction. So they pass in two sentences, and then they ask the model, are these two sentences like going one after another or not? So they use these two tasks in an unsupervised way to train their BERT model. BERT stands for bidirectional encoding something with transformer model. Yeah, I don't really remember it, although I use it. So self-supervised learning, as I said, usually in case of text it's language modeling. Or in case if you want to do a translation model, it would be cross-translation, so cross-lingual translation. A paper from Facebook does that. That means that you have some data in English, let's say, some data in French, and then you try your model to translate the English sentence to French and then back again. So you're doing this kind of back translation. It works usually, but the main idea is that you still need usually some sort of like classical supervised approach together with these methods, because otherwise it's less stable to train. Okay. Semi-supervised learning, mix match, and UDA, they are actually universal. You can use them for text too. Snorkel also. You just provide your heuristic function and it does the job. So with weak supervision, Snorkel, weak supervision, yes. Knowledge distillation. There is a recent paper that tries to distill the knowledge of this big language model BERT into a smaller one. It's made by a company called Hugging Faces. It's called Distill BERT and it was published a couple of months ago. So you should really check it out. I mean, it's quite innovatory for language models to be distillated. It's something new. Usually it was applied only for vision. Okay, transfer learning. Classically in natural language tasks, you wouldn't really do transfer learning, but rather there is a technique called embedding. So you can try to learn a representation of your natural language data set, and then use vectors from this representation and use these vectors to train your actual model. So use these vectors as features. This was the approach introduced in 2013 by Mikolov. Yes, he was his name. It's called word-to-vec. And then after that a lot of to-vec developed. But now, starting with a paper from Sebastian Ruder, if I'm not wrong, it's called Universal Language Modeling Fine-Tuning, so ULM-FIT. He was the first to try to model the language in an unsupervised way and then the model to transfer learn it actually. And he succeeded, and after that started all this GPT and BERTs and all of it. So you can do transfer learn in natural language processing. And data augmentation, it's random word removal, it's synonym replacement. Yeah, at least these two I'm using them. And there is a technique outlined in mix match, no, in UDA, they use so-called TF-IDF word replacement. So they replace the word in your text corpora with a word with similar weight from a TF-IDF matrix. Yep. Other questions?
What type of framework do you use for all these problems?
Sorry?
What type of frameworks do you use for all these problems?
I mean, if you want to get really technical into code, you can do that either in PyTorch or TensorFlow. I mean, there is no library or framework that will give you this already implemented. You have to either steal code from GitHub or do it on your own.
For example, FastAI framework, do you use?
No, I don't, but FastAI, yes, does have quite a good set of tools. And but their tools are just transfer learning.
Yes.
Yeah. I don't use them. I like to have more control over my experiments. Yeah. Other questions? No?
Thank you again.
Thanks.
Detailed answers to our questions, and let me nice certificate.
Thank you. I'll put it here and run for my channel. Deja o asta o surpriză. Atunci,
Stop. Okay, before starting, I would like to take the opportunity to thank the local organizer for this kind invitation. I will talk today about a new result obtained by my PhD student, which is called Kauta Benanin, and with other colleagues of mine, Mr. Brzaru, Younes Benani, and Issa Farih. Mr. Brzaru and Issa Farih will present some works later today. This is the little plan of my talk. The first chapter, I will give some motivation of this work. After that, I will present some classical results about NMF. NMF is non-negative matrix factorization. I will end with some experimental results, and I will talk about stability in NMF. Let us consider some sentences from 5 documents on internet which contain some keywords which should be in boldface but which are not. And we have some documents which contain some phrases with some fixed keywords. From this information we can build some matrix about on the rows we have the terms, on the columns we have the document, and we can have the query, find the document containing the term 1 and term 2 in databases. This is a very simple example, and in true life, in real life, we have an application where the matrices are huge, and we have a lot of number of terms or a lot of number of documents. Another problem is to try to find in such databases a document which is primarily interested in the first term and secondarily in the third term, which means that the matrix problem can be modelized like this. You consider your databases matrix, and you multiply by a query, which is a vector with some weights for the first term and the third term, and you are not interested in the second term. And you have some multiplication, column vector matrix multiplication, you can get the results of your query. Another example, when you have some quality air station that measure the quality of the air of some region, you have a lot of numerical measurement about the temperature, the pressure, and others type of variables, and you have signals which are over-determinate. You have many samples, and you try to understand this data. The question is to understand how this kind of numerical data can be interpreted, how to try to extract some information of this kind of data. You are interested when some phenomenon occur or not, if there is pollution, if this pollution is related with other factors, and so on. This is the, how to say, classical or typical example. Our model is based on a matrix. We can talk about matrix in image processing like before, also in text processing, also in signal processing. Always we have a matrix, and we always in this talk we will consider that we have a MN matrix, M standing for the number of objects, and N for the number of variables. We refer by AM to the M row vector, to AN to the N columns vector, and of course when you have two indexes you refer to the element of the matrix. We recall some information about matrix from basic algebra, which is a rank of the matrix is the maximum number of columns which are linearly independent. This will be important for us. Why NMF? Why non-negativity? Since it's very natural in true real life application. The physical measures are always positive, and so can be considered as positive. This, in some sense, is a restriction. From basic algebra point of view, this is not a true problem, but for us, this will be a very interesting approach. Also, in clustering or classification, we are interested in probability or try to find factor with which say, okay, which probability some data belongs to some clusters. A probability is always positive, which means that it's natural to impose this kind of restriction. In clustering, we have data, and we try to separate or to find groups in this data with the following condition. Try to minimize the inertia, the energy in the cluster, and to maximize the inertia interclusters. There is a difference between unsupervised learning, which we talk, I try to present here, and the supervised learning, which was the subject of the previous lecture. In supervised approach, semi-supervised approach, or weakly supervised approach, you always have a professor, a master, an oracle, which give you some labels. In unsupervised approach, you don't have this master, which give you some, which is able to give you some information about the true labels. You only try to find groups within your data and try to identify correctly these groups. This is an example of Cummings approach, which is a very known techniques in unsupervised learning. You start, of course, in my example, which is a very simple example, clustering. The best clustering algorithm is our eyes, our human eyes, which give you the right answer. We have 3 clusters which are well separated, which are linearly separated. Try to modelize this for computers, for artificial intelligence is still an open problem. Of course, in Cummings, the iteration out like this. You start by fixing randomly some centroids of your clusters, and you determine by using the Euclidean distance the appartenance of each data to the fixed clusters, and after that you update and reupdate iteratively your centroids and the how to say this, the partition matrix. At the end you have a well separated data, but of course this answer can be given by our eyes easily. The problem is to how to modelize by a formal mathematical model this kind of problem. In NMF, non-negative matrix factorization, we try to decompose or factorize our data matrix in 2 factors, F and G. F, the matrix of centroids, and G, the partition matrix. Of course, by using knowledge from basic algebra, you know that matrix product is possible only if the number of columns of the first factor is equal to the number of rows of the second factor. Which means that we try to decompose our matrix, which is Mn, in a product of 2 matrices, which are Mk and Nk. And by transposition, we get a Kn. And K will be the desired number of clusters. We have by using these formulas. Actually, NMF is a low-rank approximation problem and can be represented by this kind of optimization problem. Try to find x minus fg transposed such that f and g are non-negative, and try to minimize the Frobenius norm. The Frobenius norm is a matrix norm which is defined like this. And we know that this problem can be well approximated by this formulation. We will see in 1 second why we are interested in this kind of formulation. Let us reformulate our Cummings problem. In Cummings problem, we minimize this kind of functional. Of course, with the J, the partition matrix, and F, the centroid matrix. And with this kind of notation, the functional in Cummings write in this form, which is closely related to the NMF functional. The only difference is that you have a square factor. How to compute this kind of factorization? There are two classes of algorithms. The first one is the multiplicative algorithm, which is a convex analysis approach with a gradient descent strategy. And we have a little trick to define the update step. And the algorithm starts by a simple initialization at random of f, and after that we iteratively compute f and j by using this multiplicative formula. Here the circle signifies that the multiplication is a component-wise multiplication. It's very easy to implement. We don't have any proof about the convergence of this kind of algorithm. The main advantage that once a value is null, it's zero, it stays zero until the end of the algorithm. Another approach, which is a least square approach, is the alternative listed approach. Again, you start by random initialization of f, and after that you solve alternatively two systems. The first system is here in f. You solve this system in f. Once you get the solution for f, you set all the negative values to 0. After that, you solve this system in J, and again, you set all the negative elements of the solution to 0. And you will do this for a number of iterations, which should be prefixed. Main advantage of this approach is that it's very fast. We have very good results. You obtain some solutions which are very sparse. In text unsupervised learning, this is very important, to have solutions which are sparse. And we have, for this kind of approach, a lot of improvement today. NMF type of decomposition are three classes. The first one, which I already try to define, we try to approximate our matrix by this product such that the Frobenius norm of the differences is minimized. Another type is the NMF orthogonal, and you add a constraint on J should be orthogonal. You can also add this constraint on F, and you obtain a 3 NMF, which is solve the same problem with 2 supplementary constraints. The true problem in NMF is the following. Assume that you have a matrix D which is inversible. This means that if you are able to define an NMF Fj, this by simply adding your diagonal matrix, which is positive, which means inversible, you can redefine another NMF, which means that you don't have uniqueness. If you don't have uniqueness, you don't have stability in NMF. The problem, if you don't have stability, which means that your convergence could be slow in some situation. In order to solve this kind of problem, is to define a good initialization step for your NMF algorithm. And a good solution is obtained by using singular value decomposition of your matrix X, which is identical to the principal component analysis of your databases. The solution we try to propose here for this problem, which is the stability, is to use an approach of collaborative clustering or collaborative unsupervised clustering algorithm. In collaborative clustering, you try to collaborate, to define, formally speaking, a collaboration procedure between several clustering algorithms. This clustering algorithm could be of very different nature, could be of the same nature. This will be the case here. And the problem is kind of different from the consensus problem. You have several clustering results. You don't try to get a consensus solution, which could be a good compromise of several clustering solutions. By collaboration, you try to improve for each algorithm the obtained solution by using the information of other algorithms. In collaborative approach, when you try, it's by definition a fixed algorithm, a local algorithm, try to use the information from a distant algorithm. But for reasons which are very clear in true life solution, you don't have access of the data of the distant algorithm. Maybe you have only the solution of the distant algorithm, which means that you try to make this improvement by using only the solution of several algorithms, local and different distant. And for the local, for the fixed one, you try to improve by stealing some information from other distant algorithms. When you deal with medical data, this is clear. This is a problem of confidence. You cannot use a database from a region to the other region to do transfer learning or collaborative or consensus. You can do it, but using only the solution, using only anonymized data, which will be a subject later today, or using other approach, like probabilistic approach, to define collaboration between solutions. We have three classes of collaboration. The first one is the horizontal collaboration. The second one is the vertical, and the third one is the hybrid, when you mixed an horizontal and vertical approach. In the horizontal approach, what's happened? The data share the same number of observations, which means in terms of linear algebra you have the same n number of rows. In the vertical approach, you don't have the same observation, but you share the same number of variables, which means that you have the same number of columns. Of course, in the hybrid one, you mix all this information. In practical application, this constraint concerning the same number of observation or the same number of columns, it's not easy, this constraint is not easy to satisfy, which means that, but we'll not talk now about this, we should be able to take into account situation when this number of different rows or different columns are different. This is the definition of the collaborative functional. This is the formal definition. We suppose that for two different algorithms, L, the local, and the distant one, L prime, you define a matrix beta, which is an a priori information that you have about the collaboration between the local algorithm and the distant one. And with this, for the local algorithm L, you define this functional, which means that you add, of course, you always minimize the local NMF functional, and you add something, you penalize this term by this one, where this collaboration term between LL prime take into account the following information about the partition matrix of L algorithm and L prime algorithm. By this definition, we have an horizontal approach, which means that when data belongs to some cluster in the L local algorithm should be belonging to the same cluster by the solution obtaining by the L prime algorithm. In this problem, what we try, which means that we try to minimize the distance, the Euclidean distance between the matrix partition of the L algorithm with respect to the distant algorithm L prime. And for this reason, you have here the difference between the L and L prime algorithm. And after very simple manipulation of matrix, you get this update formula for G and F. Sorry, here is W, this should be an F. Here, for tools that know Cummings algorithm, here you have the partition matrix of the Siemens algorithm, which is a soft version of the Cummings algorithm. The formula are not so, how to say, are very long, but are very simple to obtain by simple derivation of matrix vector derivation of the gradient, we get easily the update rule. This is the strategy. The collaborative NML algorithm, right like this, you initialize all the centroid set F randomly. In the local step, you do an NMF for each local algorithm. And you will be, of course, intrinsically minimize a functional NMF, type of NMF. After that, you have the collaborative step, and you will update all the partition and all the centroids matrix by using the huge formula presented before. And after that, you will, of course, test your approach. But before entering in this chapter, which is the experimental results in unsupervised learning, when you talk about unsupervised learning, since you don't have a label, which means it's not easy to define, a quality indexes, an objective quality indexes, which give you the information if your obtained results is good enough. The only thing that you can maybe modelize is the to minimize the inertia intra-clusters and to maximize the distance between interclusters. And with this kind of approach, there are several quality indexes in unsupervised learning. And here we are interested in purity index and silhouette indexes, which is an average measure of this property of compromise between the minimization problem, intraclustering, and the maximization problem, interclusters. And here you have some numerical results for some databases, academic databases, which are available on internet. Waveform, space-based, classic one, and we consider the following approach. We have two algorithms, and we tried the first algorithm is the local algorithm. The second one should be considered as distant. And after that, we change the role between these two algorithms. And we remark here the results for the purity index and the silhouette index. And when you can see that, for instance, you have for the local NMF and distant NMF, you have some results, and after the collaboration between the local and distant, and after that between the distant and local, you see that the purity index, which is very related to the quality, external quality of your clustering approach, is a little bit improved, but the silhouette index do not change very much. Silhouette is again averaging indexes. I do not include all the consideration about the definition of these indexes, which maybe was not a good idea, but since the silhouette take into account the relation between the local and the distant, and this relation in average, in expectation, silhouette doesn't change very much. This is a good idea, in fact, since silhouette gives you information about the number of clusters, which is a good idea to don't change the number of clusters after a collaboration. You don't have you don't want this kind of change. This is an experimental results of obtained by my colleagues. You have the waveform, the class up. You have the waveform, the class distribution. You have a distant class distribution representing the relevant feature in the local algorithm, and the noisy feature representing the distant algorithm. And we have here 3 clusters, here mostly 2 clusters, and here we are not able to cluster anything. And after collaboration, from NMF to NMF1 and NMF1 to NMF2, we are able to recovering from NMF1 to NMF2 the local structure of a relevant feature. More about stability. This was our functional. I will not repeat this information. And you have here results on wine data. Again, data which is available on internet. And I simply show here the square error between 2 successive iterations in our NMF, classical NMF, and collaborative NMF. In red, you have the results of classical NMF, and here in blue-green, you have the results of collaborative approach. You can see, and it's normal, that in classical NMF you have many oscillations between 2 successive iterations. You change the problem successively. But, of course, still you have some oscillation in the collaborative approach, but in average you have that this oscillation, the amplitude of this oscillation goes to 0. They are not go to 0 so fast, but they go to 0, which means that we have, at least empirically, we can talk about a strategy to stabilize the NMF factorization. And thank you for your attention.
I have a simple question. When you have more 1000 features, for example, commins doesn't work good. What about NMF?
Actually, it is a very good question. And I will explain you why. Thank you. Doesn't work very well, commins. This is your functional in commins. This is your functional in NMF. And what I say very quickly, that this functional is well approximated by this one. The true equivalence is between the hard commins, when you have a very J is a two partition matrix, a binary matrix, and the NMF. You have a, in some sense, in the approximation term, you have a penalization. This first answer. In the hard clustering, the problems are completely equivalent, which means the NMF doesn't work very well, as commits. But in soft clustering, if you change a little bit the problem, you have a penalization tail. From the approximation matrix theory, this is not a good news, but from this penalization tail helps you to obtain better results, since you have amplitude oscillation, and in some sense it's strange. We try to minimize the amplitude of the oscillation, but an oscillation tail helps you to obtain better results. Better in terms of our indexes, quality indexes.
If anyone has more questions, you can ask during the coffee break. So we are a little late, so thank you, and I'd like to present the proofs of certificate. The next is Mr. Rozavu.
So I will start. So my name is Mr. Rozavu. So I came from computer science laboratory from Paris 13 University, the same university that my colleague Pastor Ab and my colleague Isan is here. So it's situated in Paris in France. And today I'll speak about some works we made in our team for the last several years. So I made some, like a small tutorial about topological machine learning and some application to images. So I have a lot of slides, but I'll do it quick. And just to know, there is only my name, but actually it's a collaboration work with in our team. Okay, so this is the outline of the presentation. After a brief introduction, I will speak about the problem spectral topological clustering and about consensus and the collaborative clustering. My colleague Basad gives some idea about collaborative clustering, but actually collaborative clustering is something that we use in our team because we work in collaborative and ensemble machine learning. And at the end I will show some evaluation results and the applications. So the problem is actually that we try to deal with very high dimensional data sets. And when we say high dimensional data sets, as we work with images, it contains thousands of variables. And especially when we work with very high resolution images, the variables are a lot of variables we have. So this is why the traditional methods cannot be applied here, and we also are interested in clustering. So to do k-means or hierarchical clustering doesn't work in these cases. And what we know also that there are some models like artificial neural networks or non-negative matrix factorization, single value decomposition, which works good for these problems. So what is topological learning? I will start by this presentation. We have the black points are the data and the input, and the green are the neurons, and this is an artificial neural network which tries to learn the structure of the data, and at the end of learning, the neighborhood neurons will contains neighborhood similar data. So the objective function is this one. Actually, we have to minimize this function where we have distance, Euclidean distance or another distance between data and the input x and w of the prototypes of neurons, weighted by the k's and neighborhood information, neighborhood matrix, which shows the neighborhood information between neurons. And what we have to do, actually, we have to minimize this distance. One of the drawbacks of this problem, of this model, is that for any artificial neural network, we cannot demonstrate the convergence of these algorithms, so we call them black boxes. And when I say that you have a cost function, actually it's wrong. You cannot call it cost function if you cannot guarantee the convergence. This is why if you want to do more elegant, we can use probabilistic approach, and probabilistic approach use generative topographic mapping, which proposed by Bishop in 1995. And in this case, we use the theory of probabilities to show how it can to prove a convergence of the model. So we say that actually here we have an input the latent space, which is the same like neurons, and this latent space use a function to generate this data. So what you have to do, you have to maximize the probability that the data will be generated by this latent space. And the optimization of the model, as we use here the probabilistic model, we use expectation maximization algorithm. So another type of clustering is called spectral clustering, which is very used for when we have non-linear clusters. And how it works, so actually we transform the data into a graph. So for an input space data points, what you do, you can put a matrix W, adjacency matrix, where we actually compute the similarities between each 2 points. And then we compute the Laplacian graph. And at the end, actually, we use k-means, but k-means will be used on this matrix, not on the initial data set. And one of the problems of this model is actually to compute the distance between all the points. So more we have points, more we have data, more complex will be the model. So it's very expensive to construct a graph if you have thousands or millions of data. So to avoid this complexity, what we can do, we can actually use the topological learning and not to compute the distance between all the initial points, but between the neurons. So we have algorithm here. So the first step, we can use artificial neural networks to compute the neurons, and actually then the adjacency matrix or affinity matrix is computed on the W, where these W's are prototypes of the map of neurons. So, and next is the same like in spectral clustering. Actually we construct the graph, weighted by the topological information from the artificial neural networks, and at the end we cluster this map. So for some results, of course, we don't look here to increase the accuracy. Accuracy sometimes increase, sometimes less stable, but what we want to do is actually to show that this model to propose, the computational time is very low compared to spectral clustering. So when you have a lot of points, and for waveform you have 5,000 points, the complexity decreases from 1,500 seconds to 1 second. So if we take a look at this graph, in blue we have spectral clustering, and in red, when we combine the artificial neural network with spectral clustering, you can see that until 2000 points, actually the complexity of both models remains very similar, and after 2000 points, the complexity of spectral clustering increases a lot. This axis shows the number of seconds to do the learning, and if you combine artificial neural network with the spectral clustering, the complexity remains very low. So I want to come back to now to show how we can use this type of models for collaborative and ensemble machine learning. So my colleague already shows some information about collaboration, so I want just to go quick to maybe just to give some words about ensemble machine learning and collaborative machine learning. In ensemble machine learning, you assume that you have a data in the input. You have several classifiers or clusterings, it depends if you're doing supervised or unsupervised machine learning. And you have a gamma here, which try to combine all the results to give a global result. So to do this, there's a lot of works. I mean, you can use some indexes to evaluate each result, like normalized mutual information or other indexes, and trying to optimize the result. Okay, so in collaborative machine learning, this is fuzzy C-means. For example, you have several views of several data sets in the input, and at the first step, we have no collaboration. Later, we collaborate between these results. So, just I want to go quick on this example. Actually, why we do this? We do this also because sometimes you can obtain different clustering results, and we don't know which one is the best one. So if you take a look at this slide, we have these points represent some houses, and we can obtain the first clustering result, which groups of houses is based on geographic distance. The second one is based on the value of houses, and the last one on the value and size of houses. So all three results are good. If you ask a geographer, maybe he'll say that this one is the best one, and the company which sells houses will say maybe that the last one is best clustering results. So when we don't know which one is good, we have to combine the results, to send the information from first one to second one, and vice versa. Okay, so let's take a look just quick at fuzzy C-means, how it works. This is classical fuzzy C-means. Compared to hard K-means, you don't have a hard result, but you have a partition matrix U here, and D is the distance between the points and the centers of data. In the collaborative fuzzy C-means, you have these two steps. First one, we compute the fuzzy C-means, and then we send the information between these results, which exchange the information. So if we simulate the data, for example, if we simulate a problem, we will have 2,000 points. In the upper image, we can see that we have two clusters, and the bottom image we have noisy information. And if you apply fuzzy C-means, you have the first results up here, and we can see that you have this is partition matrices. We have one cluster and the second one, and for the noisy points, there is no decision for the partition matrix, which is not good. And then we send the information between the both, what we have. Send the information from the first one to second one is this result. We increase the quality of this noisy data, and then we send the information from noisy to good one. The quality will decrease for the first data set or ensemble of data. What it means that the quality of the result what we will send is very important here. Okay, so how we can use this principle for topological machine learning? What we are doing, we add the second step here. RSOM is classical self-organizing map function, and this is artificial neural network, and we add a collaboration term. Collaboration term means that we will send information from the sequence or data ensemble GG to EE. So this is the algorithm. Of course, the formula looks very huge here, but it's not complicated to use it because this one is K is a neighborhood matrix, X is the data in the input, alpha is a parameter we will fix, and K, KE, and KGG are two neighborhood matrices, the local neighborhood matrix and distant neighborhood matrix. Okay, so we can do it for both vertical and horizontal collaboration. If you have some results, just to can look here, the first data ensemble here, you have an accuracy of 75%, in the second one, 47%. when we send information from first one to second one, the accuracy increased to 54, and from the second one to first one, the accuracy decreased to 62, which is normal. And we can do the same thing for the probabilistic machine learning. The probabilistic one, if you don't have distances here, we have matrix of probabilities. So we use these matrices of probabilities, the a posterior probabilities for the local data set and distant data set. So I don't want to stop all these problems. We have probabilities matrix, but you have also the prototypes of the neurons. So maybe I'll go, I don't know how much. Yes, I go quick to the application because I don't have time to show all this. Okay, so for the application, this is the first one. Actually, this is the application that works for last 7-8 years in different projects. In this one, we have the example of the satellite image. This is one image, and this image corresponds to Strasbourg city in France. This is the Rhine river, and after the Rhine river is Germany. So what the goal is to try to cluster this image in order to obtain different clusters like vegetation, buildings, roads, small vegetation, high vegetation, water, and so on. So how we apply these models that we proposed. Why we need the topological and collaborative clustering here? Because this image is described by different features. So you have spectral features, you have pixels information, but you can have some more specific domain information like some indexes like humidity index or distance from one pixel to the Rhine river and so on. So different information which you can compute. So this is hard to see because a lot of pixels is very high image here. But you can see that, for example, water is well detected, and some water also roads are detected here. And if you don't do collaboration, for example, this one is a road here, blue. You have seen that there is a yellow because you have this yellow orange yellow here. After the collaboration, it becomes blue or blue. And the second application, what I want to show, is to do it on the Wikipedia images. So what we have 20,000 Wikipedia images, and want to try to browse, to make a system to browse these images. So if you take a look on this example, if you search from the Google or Yahoo, you search for an image, for example here, Flag France, you obtain this result, 30 million of images, which is good that Google has 13 million images, but you don't need 30 million images. If you want to browse all the images, if you need 2 seconds by page, actually you need 15 days, day and night, without stopping to browse all the 30 million of images. Of course, if you look for a flag, you can take the first one, but if you look here for right here, for example, landscape with the mountain, maybe the last image will be the good image. So what we propose to use the topological artificial neural network and collaborative clustering, and indeed usually when we visualize the artificial neural network, we use this type of images. For example, each neuron have a color to indicate to which class belongs this neuron. But we cannot. But in our case, for images, we can visualize it using this schema, and to show that the topology is respected. I mean, you have flags in this part, blue images in this part, white images here, for example. So what we can do later, we can click for one neuron to have all the images from this neuron, or we can browse this system because we can look at it, this artificial neural network like in 3 dimensions. Why in 3 dimensions? Because if each neuron captures some data, we can sort this data in the neurons, and then we can browse and to see all the images which contain this the system. I want just to show maybe. A moment. Not sure it was. So this is the system that we made, and just quick I show this system and then I stop. We made in our team with our colleagues several years ago. So what we have two artificial neural networks we computed using weighted distance and batch distance, the batch model. We will do the two things. We make a classical clustering to show the difference between classical clustering and topological machine learning. So this is the artificial neural network result. It's a map containing 169 neurons. We put 13 by 13. Why 13 by 13? Because if you put more neurons, it will be very complex to visualize the system. Blue bars here show the cardinality of neurons, shows actually how many images you have in each neuron, and the bar here allows us to browse the system. You can see that the topology is respected. You have blue images here, flags, red images in this part, and so on. So when you browse the network, what you have that you will obtain empty neurons because the neurons capture a different number of images of data, so it's arrived at, I think, at 300 step. We have only one neuron which contains images. Okay. So this one is the classical clustering result. So it's very hard to analyze it because you can have red clusters divided by different white or blue clusters. So it's not intuitive results. It's hard to help the user to browse this type of information. When you go back on this one, we have the keywords also. So if I put here in French, I put drapeau, we will show all the neurons which contains images corresponding to flags actually. Red means that you have a lot of images. Blue means that you have several images. And of course, we can browse the system, or we can click on cluster on the neuron, and we will obtain the, for example, like here, all the images captured by this microcluster of neuron, and we obtain. And next, we found the image we need. We click on this image, and we go to the Wikipedia page. Okay. So. Just to conclude, maybe. Yes, just to show you why we need to use ensemble machine learning or collaborative learning, because for these images we have one image corresponds to one vector which is the size 6,400 values, and we have two types of information: colors and texture. And we have another data set which contains the keywords for each image. So actually we have three matrices, three data sets, but for the same problem, from the same distribution. 20,000 images and 6,400 variables for colors, 20,000 and 6,400, and this one will be 20,000 to 2,485. And the last one is very sparse data set because contains a lot of zero. This is why we need to combine different models like spectral clustering, topological clustering, and collaborative clustering. Okay, so I'll stop. Thank you.
Thank you.
Have questions?
Same as someone questions you can ask during the coffee break because we are late.
Yes, we are
So
late.
thank you very much
Thank
for
you.
the presentation.
Thank you. Okay. Thank you.
So next session after coffee break we start the same time. I mean, in 15 minutes or maybe later.
How do you want? Might be later.
11h30.
And coffee break is here? Thank you.
parts explained in one XML document. Each one suspicious, one XML document. Here is an example how there is presented one span of plagiarized text. Actually, there are when the plagiarism started and how long it is in characters. And from which document this part was taken. Again, when it started and how long it is. Something like this. And a lot of text, just text and text format. And what have students done? They used normalized compression distance to compare documents and to find if in this suspicious document can be some plagiarized fragments. So here is this the formula for this method. Here is more explanation. So if we have two texts, we compress one text and second text, and we compress them both combined. And then we use formula to find this distance. And if the texts are similar enough, this distance is small. If they are quite different, the distance is much bigger. So actually, the smaller is distance, the more probably the texts are contain similar parts, something like this. And then this some technical information what they use as parts of their code. And the first step, as is all methods that were used for this task, the first step were to detect if this suspicious text has some plagiarized parts. If this distance, normalized computed distance, is small enough, we consider that there are some parts. And then the text is split in sentences, and each sentence is checked apart if it is somewhere in source text or not. Something like this. For the sentences is used the function similar text. The actually flow was this method, but well, it's done by students. Those thresholds that are assigned like empirically based on the data they have. So we can say this method can be ported easily to other texts. So they found those thresholds on the based on data. And actually performed the experiments, again just working with only 40 documents, they obtained the best results ever. Well, maybe they selected those documents to show they can do this. What have been done on this task by other participants when task was called in 2009. 10 teams participated in the challenge and proposed 10 systems, and they also used two-step algorithm. First to find which suspicious document have some plagiarized stolen parts and which not, and then to find those parts in the documents. Using various metrics for similarity between documents. And the results on all the data, for the best, this one is the best result for all data during the challenge. But it should be mentioned that actually when the test data is released for the teams, the results are slightly worse than when you experiment with the training data. So we can see that the results are not that high, 70%. Comparing with our results when actually almost 100. And well, it's a message for the students. So, if you have the questions.
How do you get vector? And then how do you calculate some distance?
They used the whole text and calculated the distance between text.
How do you get vector? One coding, TF, IDF, embedded.
No, they use just the whole text and compress the text. And this is a measure. They didn't make all this operation on text. This is actually the best part about compressing methods. There are a lot of compressing methods that measure distances between text, and this is the best way. I mean, you don't need to manipulate with text, you don't need to pre-process it, you just compress it. That's all. Like a string of characters.
Thank you again.
Thank you. From the Paris University.
Hello everybody, my name is I am an assistant professor at the Paris Descartes University, and today I'll present you a work based on data anonymizations. It's work done by my PhD student Sara Zunina and another colleague, Younes Benani. So, what is the motivation of this work? In fact, nowadays we have a lot of data collected by sensors, social networks, connected objects and mobile applications. And of course we need to collect, to treat, to explore and to transform and to learn a lot of information from this data. So, we have the desires of governments to open their data as a proof of democracy and good practices. Of course, I think you heard about the privacy breaches of the last decades as Yahoo scandal and the Target scandal. If no, you can read it. I think you heard it. So in this case, it will be very interesting to anonymize data in order to be able to show this data to the public and to be able to treat this data. So, what is important in this case, we should be able to anonymize data with a very low re-identification rate and with a lot of quality for the analytics. So the data after the anonymization should not be very poor. Okay, it should be able also to be analyzed by the scientific people. So, for this presentation, I will start with the part based on the state of the art. So I will present you the main approaches, and after that I will present you our contributions. So for the main approaches, you should know that we have three groups. The very basics, the randomization methods. The other group is the group-based methods. They are interesting because they are close to the idea of the clustering. Okay, so and we will show some methods based on privacy preserving on data mining. So for the randomization methods, you have two fields. You have the very simple way. In fact, so you can add some noise to your variables. You can make some substitutions, some suppressions, randomization, and so on. For the non-perturbative methods, you can do it also by generalization, shuffling, or tokenization in two ways. So they are very simple methods, but not very effective. Okay. For the group-based methods, we have very classical three methods: K anonymity, L diversity, and T closeness. I'll give you an example. So I have, it's a real example. I have two data tables. So I have medical data and a voter list. If I will cross these two tables using only these three variables, zip, birth date, and sex, I can find the identity of the person. So if I'll use it separately, I will not be able, but if I can have both data table, by crossing this information, I'll have the identity of these persons, okay, of all the persons. So, in order to avoid this kind of situations, what we'll do, we'll use some methods. I'll introduce you briefly the K-anonymity methods proposed by Sweeney in 2002. So the idea of this kind of methods is that a table is said to have K anonymity if every record is repeated at least K times. Okay. Of course, what means data anonymization in our opinion is the process of de-identifying sensitive data, preserving its format and data type. So, to explain these methods, we'll need some information, so some basic definitions. So, for all the variables, we'll have 5 kinds of variables. Explicit identifiers, so it will be attributes that identify a customer directly, as insurance, ID name, social security number, and so on. For the quasi-identifiers, they'll be represented by attributes that are publicly available, as phone numbers, mails, geographic and demographic information. Some sensitive data will be described by attributes that contain confidential information about the record owner as health issues, financial status and salary. And also we have among all the variables non-sensitive data as different kinds of data that are not sensitive for the given content. We'll take a simple example. We have 4 variables as zip code, it's in the US, age, nationality and condition. So as non-sensitive variables we can declare the first 3 variables, and the last one, I mean the disease, will be considered as a sensitive variable. So for the 4 anonymous data, so we'll have k it's equal to 4, we'll have these kinds of anonymization. So for the nationalities will be only represented as a small star. You have the zip code also, which is anonymized, and for the age we'll have only the threshold. So from the original data we'll obtain this kind of data, which is 4 anonymous data. What is the limitation of this kind of algorithms? In this case, it will be easy to find out that Bob, using the zip code, we know the zip code of the Bob, we know the age that is 37, and in this case we can find that Bob usually it's sick of cancer. Okay, so we can have a kind of homogeneity attack in this case. Another example here for Alice as a background attack. Alice is 90 years old and lives in the zip code 2001-022. So in this case, we can find that Alice is sick of obesity or hypertension. To overcome the limitation of this kind of methods, in the literature was proposed another method called L-diversity in 2007. So we have the previous table, if you remember, the 4 anonymous data, and in this case we will add some diversity at the degree 3. So in this case, what we will do, we will mix all the individuals, so you don't have the same order. And in this case, it will be more difficult to find out the disease of Bob. In fact, here we'll have 3 options: hypertension, obesity, cancer, and so on in each class. So we have a 3 diversity in each obtained class. Of course, for this kind of methods we have also some limitations. So if we have these 3 kinds of cases, so if we will analyze from left to right, in the first case we will see that 99% of the population is healthy and 1% is sick, so it will be easy to find out this 1% of sick persons. The other one, the second case, we have half of people that are sick, half are not sick. And the third one, what is presented here, that we have all the 3 diseases that are related to stomach problems: gastric ulcer, stomach cancer, and gastritis, and so on. The third method that belongs to the group-based method is T-closeness, presented in 2008. What is the idea of these methods? So we can say that a class has the T-closeness if the distance between the distribution of a sensitive attribute in this class and the distribution of the attribute in the whole table is less than t. So we will fix this threshold t. So in this case we'll say that a table have t closeness if all equivalences classes have t closeness. Like, what is the principle? So we have the first assumption. So Bob is sick. So Bob has hypertension. 25% of the population has hypertension. So Bob is in the 25% of the population. Bob lives in this zip code 2000 and so on, and is 30. So in this case, and Alice know that 30% of his class has cancers. So in this case, we can find out that Bob has hypertension. Yes. So also in the literature we have some methods that are adapted to the clustering. So hereafter I'll not give you more details, but you can read. Hereafter I'll skip the slides. We have 3 other methods based on the group-based methods. So K-member, canonization, clustering in attribute hierarchies, and clustering-based greedy algorithms. Okay. So, what we'd like to do in this case? So, we'd like to anonymize data automatically and without much hand engineering. Evaluate the anonymity-utility trade-off. And of course to use efficient techniques to anonymize data, but without much loss information. So for that we'll use the collaborative topological clustering presented before by my colleague. We'll use the idea of the multi-view clusterings, which will allow us to deal with high-dimensional multi-source data. And why we are using this kind of approaches for the anonymization? Because if you have better clusters, in this case we'll have a better information preservation. And another idea that we'll use for the anonymization is that we will code data using the cluster prototypes of each view. Okay, we'll use this information. So, for this kind of problem, we will propose 2 methods. The first one, called KTCA. What is the principle of these methods? So as the input we'll have D dataset to anonymize and P number of views, and at the output we'll have the anonymized data D1. So we have 3 steps: multi-view clustering step, pre-anonymization, and fine-tuning and anonymization. So for the multi-view clustering step, we'll start by randomly generate P views, and after that to create a sum for each view. And after that we'll use a collaborative algorithm for all the views. For the pre-anonymization step, we will find the best matching units for each object in the view, and we'll code our dataset using the BMU. So the result will be coded in the D1. And the last part, we'll build a global sum using the anonymized data D1 find the BMU for each object, and we'll recall the data set, and we'll evaluate the k-anonymity level of D second. For the second method, we'll use the linear mixture of the reference vectors. Usually Conan use the Wiener neuron principle, but for the second method we'll use another kind of approach proposed by Conan using the linear mixture of the reference vectors. So for the other methods, called constraint TCA, we'll have the same 3 steps, and what is different in this case, we'll find for the pre-anonymization step, we'll find the linear mixture of some models for each object, and we'll use this information for the last step. Okay. As an experimental result, we used many data sets. These data sets are public data sets, so you can use them from the UCI repository. What you've done in this case, we took the original and the anonymized tables, and we used a decision tree model with the T-fold cross validation to evaluate the utility of the anonymized dataset. So, in this case, we will present the accuracy of the different tests on the pre-anonymized step. So for all the methods, we have the accuracy for the pre-anonymized step. Okay? Of course, it's interesting in the case of the clustering to use some internal measures if the labels are not able. So in this case we use the Davis-Burdell index, and the Davis-Burdell index explains the ratio between the within cluster distances and the between cluster distances, so the similarity and the separation. So we have this Davis-Burdell index before collaboration and after collaboration. After the collaboration, the Davis-Burdell index is less, so it's improved. Hereafter, you have also some experimental results for these 2 methods. So the accuracy and the k-anonymity level after fine-tuning as described in the first method, and here the results for the constraint TCA method. As conclusion, I will say that the anonymization will allow us to present data to the public. Okay, it's also interesting to use it in the case of the universities to show the results or some information on the students. And in this case, we'll need some anonymization techniques to provide some open data. So in the literature you have many methods, as I presented earlier. In our case, it's interesting to use these kinds of methods in the field of the unsupervised learning. So that's all. Thank you. Questions?
How do you do validation of our models?
Your models or mine?
Your models.
Okay. In fact, how we are doing the validation, what we can do, we have some papers that used also these data sets, so we can compare the results with the results provided in the other papers, okay? And of course, to evaluate the quality of anonymization algorithm, we have many measures, and it's still an open question, you know, which measures is better to evaluate the quality of the anonymization. In our case, it was only the accuracy of the methods. And
but why do you use decision tree for calculate accuracy?
For the decision tree, we'll use it because we have the labels, so you can see if our techniques done good results compared to the
Decision tree only one tree or random forest?
Not random forest. I mean,
One
yeah.
a lone tree. Okay. Maybe good approach, for example, if we use neural networks for maybe predict some ID, some users in your data set, and for example, first step training neural networks, and then pre-mutable your data, anonymize it in data, and send this data to neural networks and analyze some predict neural networks, good or bad for your data. Maybe this approach is useful for your task or no?
So you'll predict some results and you'll compare with the results obtained by...
Maybe use neural networks for guess real data in your data set.
I understand. It's an interesting idea. We should see how to do it, in fact, how to compare it. Yes, maybe.
Thank you again.
Нет, мне просто непонятно вообще. Ну, ты предлагаешь просто, ну, типа, например, то есть у вас еще будет погрешность на сеть. Сеть же нейросеть будет предиктить погрешность.
Нет, это самый смысл. Это работает как данные. Это генеративная адвертайзинг. Как научили, например, генеративная на существующих языках. Она состоит из двух сеть пытается сгенерировать человека несуществующего. Вторая сеть, это человек или нет. Там звука лучше оставила еще что-то, что нравится, если нет. Человек генерирует, опять-то генерирует, это поднимается, видите, они потом существующих людей. Но они похожи на задачи. Какие задачи? Лучше всех распознавать этих ты ему даешь уже анонимизированную структуру данных. А сеть пытается по анонимизированной структуре данных восстановить реальную шумовую подушку. То есть сделать обратно, да? То есть это уже а сеть ее вернет назад. И все, нам будет возвращаться. Требует все. И ключ ее использовать для того, что насколько уровень организации у тебя хороший. Ну, например, если ты построил дом, оставил все поля. Все красиво скажут, ну, вот этот человек. Ты понимаешь, его анонимизировано, анонимируешь еще что-то. Это же все попробуют. Как человек, то есть типа нет, это не потому, что вы так используете. Нет, я не нейросетки. Я думал, вот с нейросеткой легко использовать, знаете, как в ганах используется, когда ганы определяют типа фейковое лицо или нет. То есть вы, грубо говоря, скажи, что такое ган. И так вы узнаете. Смотрите, берете, например, какую-то запись, ну, вашу, да, сначала тренируете сетку на всех неанимированных данных, потом тренируете ее, когда, например, что-то скрываете, но все равно говорите, это этот человек, да, то есть какие-то поля показываете или нет, а потом начинаете своими методами анонимизировать данные. И на сетку подаете и спрашиваете у нее, типа, что это за человек. Если она на каком-то этапе еще угадывает, что это за человек, значит вы анонимировали еще недостаточно. На каком-то этапе более глубоком она уже начнет там ошибаться. Типа что-то в таком духе. То есть типа как бы проверить, насколько глубоко нужно анонимировать, да, то есть нужно это или нет. Потому что я не понял, как вы именно организуете с точки зрения, надо дальше еще что-то сказать. Ну, то есть можно ли из анонимированных данных все-таки восстановить кто это? Да, где вот это? Ну да, если насколько вот эту глубину можно.
Да, там как там есть качество.
Но Decision 3 по сути вы использовали просто для расчета accuracy, да? То есть оно у вас по сути считалось.
Decision 3 он же медленно работает.
Не, он
просто пока ветки переберут.
Нет, Decision 3
на больших данных плохо работает.
Не, если много фичей.
Да, много фич.
И он сильно оверфитится. То есть он может где-то там вот оверфитился. Что не какой-то рандом, если было много одиночных деревьев, он так оверфитился. Не, ну если данных много, то можно быть и так. То есть если дерево не сильно глубокое. По сути, Decision 3, если так вот математически намыслить, он очень похож на камень. Да, то есть, по сути, это тоже метод кластеризации, это чуть другое. То есть, если у вас на перфище очень много, то он уже будет плохо работать. Ну да, не, ну это от нас это зависит. Но вообще в любом случае прикольно. У нас в Украине никто не знает. У нас максимум научный. Больше никак нет. А во Франции, я так понимаю, это важная проблема, да, что надо анонимировать данные так, чтобы никто не
Это по
понял.
GDPR в одно вы делаете закон? Или это...
И проблема в том, что в университете просто хотели показать данные студентам. И не смогли, потому что есть вот эти адресы.
Мы показываем без проблем.
А тут нет, иначе подадут в суд студенты. То есть она будет личность. А то же самое в больнице. Проблема в том, что если есть только один адвокат, даже несколько,
Тогда их можно вытянуть с них. Где-то они на пересечении, иначе. А что, больницы должны хранить вот так данные, или это то, что внешне? Хранят они все, а если внешнее, то должны анонимировать, да?
So the next speaker is Sam Falik from Clermont-Auvergne University.
Hi everyone, thank you Mr. So I will present our work that I've done in collaboration of Nestor and other colleagues, so namely Eros Kanawachi and Younes Benani. So I'm associate professor in Clermont-Auvergne University, so I'm working in the Limos Computer Science Lab. So this work was in a project, we call that Hermes project, with company private companies like Auchan, Numside, and also some scientific labs, namely INRIA, ELIPEN. So the data that I will talk about today is namely a multi-view data. So we have a topological networks with two these models. So we have nodes and links. We can expose we can present a complex network, complex system. For example, if we take the case of Facebook, we have users and we have links between these two users. For example, friendship, work with, etc. But we have also other information related to these users. and it's different. So we have images, we have text, we have some other attributes related to this object. And also, if you take, for example, the case of airline transportation network, so we have nodes that are airports, and they are linked between a company and an airline company, and also for collaboration network and so on. So our problem is how to cluster this type of data. So the clustering problem is to identify some group of similar nodes in a set of objects. So if we check, for example, the Lazaga-Low third network, so it's a node network in psychology. So we have lawyers, we have information about each lawyer. So for example, statute, gender, office, law school, and so on. And we have different relations that link these lawyers. So we have co-work, advice, so a lawyer take advice from another one, and also we have friendship. And how the problem, so how can we cluster this data that we call attribute networks, because we have attributes and we have also the relationships between them. So the idea is to take at the first time, so the different relationship between nodes. So we call that multiplex network, and after that we can add the second information that are the attributes. And also the other problem, how we have a clustering result, but how can we evaluate that? So the idea is we have external and internal indexes, but we can also take a type recommendation, type-driven evaluation, which is in my case the recommender system. So let's take the multiplex network clustering. So we take the same example. We have lawyers and we have information. So we recall only the different types of information, and we stand by this information, this additional information. So a multiplex network is defined by a set of nodes, the same node over layers, and we have also the different layers differ by a relation. So if we take the same example, we have here a graph, a network that represents only the friendships between lawyers and co-work and so on. So we can have many graphs, many layers sliced by relation. And there is also the coupling links. So if the links are moving from one lawyer to another to the same one or to another one. So we have both types of information. So the state of the art of attribute network clustering can be divided by two principal trends. So we have approaches that transform the problem to a problem of complex network by layer aggregation function approach or partition aggregation approach. For the first one, layer aggregation, so we have the divergent view of the network, so layers. So, and then we apply an aggregation function. For the simple one is if there is a link between these two nodes, it will be in the aggregated layer, and then we apply clustering for graphs on this aggregated graph, and then we found the result, the final result. The opposite one is I will apply at each step, at each view of the network, a clustering on graph approach, and then I will make with an ensemble clustering method, I will find the result. Or I can generalize an approach that it was designed for a simple graph to the case of multiplex network. It was a case of Musha that generalized the monoplex modularity, Newman modularity. It was a case of the simple graph to the multiplex graphs. Multiplex graph. So with using some with different layers between the multiplex network. So, but this approach has it's rely on the modularity, and the modularity it is based on three principal hypotheses. So the first one is that the best partition of the graph is the one that maximizes this modularity. The second one, if a network has a community structure, so it is possible to find a precise partition with a maximum modularity. And if all the maximum modularity that we found that must be similar. And all these hypotheses do not hold. It was proven by Fortunato and Mentenance that this hypothesis was wrong in the first modularity. So here we need to search for another alternative approach. So we propose a maxi-code algorithm that is based on three principal steps. So it's a synthetic algorithm that was designed for very large graph. So the idea is I will look to leaders in each graph, in the graph, and then each node will rank his list of leaders by its own preferences, then based on the shortest path. And then the third step, it will be each node modify its vector of preferences of neighbors his vector by his neighbors' preferences by using rank aggregation methods, namely Borda or Kemeny. We experiment that on 4 data sets that is 3 layers, that multiplex networks. It is based on 3 layers and different nodes between these data sets. So we find based on redundancy, that redundancy means the defined cluster must be redundant in each layer. So we compare between the 2 principal approach, basic approach, namely layer aggregation, partition aggregation, and the one that maximizes modularity and our method. So we see that this method give a better result in terms of redundancy than classical approach, and our proposed approach give a better result than the one that maximizes the modularity, when we call that. And in terms of complementarity, the same result. So let's move now to the attribute network clustering. So we add also the attribute information on each node. So here we take also consideration with this information instead of different link. So here we define an attribute graph by 4 tuples. So here we add a set of key attributes for each node. And if we take the union of all attribute vector, is the vectorial representation of each of the node sets. So the problem is we have to find a hard clustering, and also the nodes that are in the same attribute, in the same cluster must be densely connected in terms of structure. So here is the topology, and also they have to share the common or similar attribute value properties. So the state-of-the-art of attribute network clustering can be divided into 3 principal chunks. So the one that transform the problem to a topological based clustering, or the one that transforms the problem to an attribute based clustering. So we propose an approach that is also in the second main trend. So we have with the same idea, so we select in each layer a set of attributes, so we call that point of interest, and then we know that we have a very large graph, so we have to reduce the size of this graph. So we're gonna select a set of points of interest to reduce the size of our graph and each slice, and then each node will be characterized by its relation to this point of interest. And then we're going to incorporate by weighting the seed feature that we found, the matrix of point of interest, and also the node attribute feature. And we're going to normalize, make some matrix factorization, and then apply unsupervised learning technique, simple one, Cummings, for example. So here, we form the membership matrix by defining the shortest path between each point and the point of interest. Then we make a similarity matrix between each attribute value, each vector of attribute value of each node, and we find the largest agent vector for each matrix. Then we combine them and we apply Cummings after. So we apply that on 100 synthetic data. So we compare between Cummings that take only the attribute value, so the information only about the attribute, no structure here, and we take Louvain and we compare with Louvain and Worldwide that take only the structure, and we compare with iLouvain that take both the structure and also the attribute information, and our proposed approach in blue here. So we found that topological structure gives better result in terms of with Cummings, and if we take both information in consideration, so we have a better result than taking only one separately, and our proposed approach will give a better result in 100 scientific data. Let's move now to validate our approach by an application. We take the case on the of recommender system because it was in the project, in the context of this project. So the problem of collaborative filtering in a recommender system can be the flow. So we have a rating, we have different users, and you have different item products, and each user have a rate with a manner. So he like or he dislike in a scale of 1 until 5. 1 if a user dislike an item, and 5 if he like it. So, and the problem is we have to fill this matrix. So that we call user item matrix. So the predicted method will be I will make a clustering firstly on the user to have a profile the user, and then the second clustering it will be on the item. So we have a set of a clustering on items, a set of items that share the same property, and then to evaluation. So we fill the matrix. So we, for example, what will be the rate that will be given by user 2 to the item I7. So firstly, we will find the corresponding cluster of user U2, and the same one for item I7. And then we find this, for example, and we'll apply an aggregation function, for example, the mean, the mode, or the median, and then we're going to find the predicted rate that will be given. So, but the problem relies principally on the clustering step. So how we do the clustering? So we will validate our method here. So we apply that on movie lens data, so it's a known, very known data. We have 100,000 rating from 1 to 5, given by approximately 900 users on 1,060 movies. So each user has rate at least 20 movies, and the data at which to make some cross-validation approach. And we have some attribute information about user that are age, gender, occupation, and also about the movies that are the genre of movies. So action, adventure, or comedy, crime, etc. So we have this bunch of information, and we have here that we make our rating distribution per learning base. So here we find that there is few rating of items that a user dislike, and normally we buy or we saw a movie that probably we like. So there is many rating for that are given by a user who give for example, in the 4-base learning base. So the evaluation criteria that we know in the case of recommended system, so the mean absolute error, the root mean absolute error, and a precision report. So we apply that on Mentenance. So the user item matrix for to have a multiplex, so can be seen as a bipartite graph. So here we have users, and we have items, and we have each color correspond to rate value. So firstly, we dissociate each rate value. So we have 5 bipartite graph. We make a projection on users and then on movies, on items. We have a multiplex of 5 graphs. So each layer corresponds to a rate value. So from 1 to 5. And so this is the visualization of the obtained multiplex network. And then the result that we found that using only topological structure here. So here we use only topological structure. Can use only the attribution information. The topological clustering, so they make on the same cluster movies and also users. And the one that use our proposed approach that use both type of information, namely the attribution information and also the structure. And we obtain that using both type of information increase the result of recommender system. So as clustering, so we saw an overview of existing approach of attribute network and multiplex network clustering. Clustering based recommended system, we propose this approach, and clustering results give a proportion result. So we can find the error package for both multiplex network and also for attribute network clustering. So it's also available in GitHub. And thank you if you have some questions. Thank you. Welcome. Any questions?
Some questions.
Yeah.
For example, if some users like anime movies, then maybe they will take a high score for animal movies. Do you use some additional features that characterizes some group of users like movies, animals, some more like some detective and other. Some features for intercept your decision function. You intercept your decision board.
Before making the clustering?
Yes.
No, we check both information. So the information about, for example, comedy or crime movies. So we check that, we add this information to the topological structure of the network.
For example, this movies is bad.
Yeah.
But some group of users only like anime movies.
Yeah.
But this movie is bad. But this group users usually take a high score for any anime movies. Some intercept for this group, some features for this group users. Do you use or not? And why?
So we use that implicitly by using the multiplex network. So here, for example, what we said. So, for example, if they are users that will prefer, for example, they make a higher score for animals movies. So here, what we said, we just said that 2 users are linked if they like the same movie, and they make this they rate the same movie with the same rate. So if they like it, it will be. They will have a connection here.
Okay.
So we make and if they are different, for example, they are not crime the same users, and they like, for example, crime movie, so they also be linked. But here we have, that's what I don't say, that we have a weight between these two users. So how many films that are rated, that they rate with the same rate. So, and then we filter by, for example, if they have 10 movies, and we take only 2, and if there are only users that less than 8, it will not be linked in the multiplex network. So it's a way to do that. Yeah.
May I ask, thank you for the presentation. According to this question, actually I want to add another one. So this is one point of view, but from the another point of view, we can hire some children or some students in India, pay them, and they will rate our films according our marks and so on.
Yeah, that's another problem. Yeah, because only for ads on Facebook or on Google, they all, namely in YouTube video. So if there is a actor that have or a singer that share a video, so they are Indian person or I don't know, everywhere in the world, they are paid to like or to watch this movie. So here,
about Indian people, I just kidding. So I mean that actually you can do it manually. Just hire 100 people.
Yeah, but
or you can provide the new business. So you register for this.
This workflow.
Yes, this register your portfolio. You have a history, and so you can sell your portfolio, or you can sell your data for that, for doing the ranking.
Yeah, but for example, if they are the same people, they have the same, I think, user. So if we take, for example, the same, as I said, if we take, it will be linked, and they have very linked score, and there is no redundancy they only like this movie. I can show you.
They will be liked. So that film for which they have a salary. Yeah. So actually, from one consumer can say for comedy, another one for Joker movie, and so on.
There are different movies, different kind of movie. Yeah. I'm alright, but they only they only rate the movie with a star of 5. Yeah, 5 stars. That's right. So, but the multiplex network, where I'm doing the community, or I'm searching for clustering, I take into consideration not only one layer. So the community must be densely connected over the different layers. So they like and also they dislike the same movie or the same kind of movies. So here, for example, they are linked here. They have to be linked here, and so on.
So it has many constraints, yes?
Not many constraints, but in our approach, so what we take in consideration that the community should be densely connected over each layer. So that's why.
Okay.
So if there is only one layer, so
it's not enough.
Not a community, so only a link that disappears.
Do you have maximum? May I ask?
Yeah.
1 second. Do you have maximum number of layers?
There is no maximum number of layers.
Depends on calculation. Technical.
Yeah. But, for example, if we take the ANCA, this one, I can take many layers, but it depends also. If I take many layers, I will reduce also the length of agent vector here. Otherwise, I will have a matrix of million columns.
And how you compute the number of layers? Empirically?
No, the number of layers is only the number of relationships over a network. So if we take, for example, Facebook, there is friendship, there is family, there is...
Okay, for EMDB dataset, how many layers did you have?
Movie answers.
Yes.
Only 5, because we take only the stars the range value from 1 to 5. So you only have 5.
Okay, it depends on the size of the data set or on the
But
type
range,
of the...
on the range value.
Okay.
Yeah. So, but we can have a big number of nodes in that case. Do you have any questions? Okay.
Continue discussion during the lunchtime. Thank you again.
Thank you.
Ну, так, например, смотри, они используют они там подсвечивают. Они поставили какой-то когда зашел, люди научили, потому что они смотрят на кого кто использует и, например, довольно нумерологи все отошли, получишь там 100 гривен, значит, вообще добро. Они смотрят, ты послушаешь, и это всегда ты на кого-то всегда просто нужно не настроить. А это получше?
So here, if we go to the internet, let's see information index. So here we have a parameter that told us that the length that represents only in the communication. So, and only in this communication. So they have to be stronger in this layer, the other layer. So if there is only one layer, also in if I check complementarity, so here we have exclusive complementarity. Classification of three measures, they may exclusive achieve the number of nodes that are in this community only in one layer, and they have in this case they will have 0 here. And 0 is very bad because between 0 and 1.
It's your criteria.
Sorry?
It's your criteria.
No, it's the complex network criteria.